Welcome to week 11, lecture 2 of Bio 6612. In today's lecture, we're going to cover random intercept and random slope models, which are both types of linear mixed effects models, as well as getting the mean and variance from these models. We're not going to talk about likelihood principles, though. We're going to skip that. So first is the random intercept model, and this is the simplest form of the linear mixed effects model. So I have a model written here, not in matrix notation, just for an outcome y. Ij is just one scalar value for the jth time point of the ith individual. So let that Yij and Xij be the outcomes and covariates for the ith individual measured at time Tij, where there are 1 to I subjects. Those are the values that little I can take, and little j can take 1 to ji, depending on the time point that we're talking about. Xij is bolded here because this represents a vector of possible covariates. That's going to be size p for the number of different covariates that you have. So the random intercept model is then written out here, where you have the outcome Yij, and then you have a beta 0, which is a population level intercept, the covariates times each of the betas for that covariate. So that would be like x beta 1 x1 ij plus beta 2 x2 ij, all the way up to beta p for xp ij, if you were to expand that out. Then this little bi is the random intercept term, and the eij, epsilon ij, is the measurement error. So we talked a little bit about the distributional assumptions for linear mixed effects models in the last slide. So that Bij is the random intercept, which is a random effect. And we assume that has some distribution. That comes from a normal distribution with mean 0 and variance sigma squared b. This is the subject-specific random intercept. Each subject has their own intercept. Then the measurement error, epsilon ij, also is assumed to come from a normal distribution with mean 0 and a different variance. The sigma squared is the variance. And we assume that these are IID, these measurement errors, which means that the correlation for the error between time point j and time point k is equal to 0, even within the same subject. And then we also assume that Bi and Eij are independent, which means that the correlation between Bi and Eij is also equal to 0. So the random intercept model describes the mean response trajectory over time for the ith subject. So if you take the expected value of the model in the previous slide, which we're doing here, it gives you this value here, and this is the conditional mean of the outcome y given the subject-specific effect bi. That is the mean response trajectory for that subject. However, if you want the marginal mean or the population level mean for the outcome, you can take the expectation of that expected value, which is equivalent to integrating out the subject-specific intercepts bi, and that gives you a mean for the population, which is what you normally see from regular linear regression, which is just going to be the beta zeros plus the beta x1 plus all the other x beta terms. I think it can be helpful to see this visually, so I have a picture on the next slide. So we're working with the same model here. that I showed you in the previous slide, the same random intercept model. I just rearranged the terms so that the two intercept terms are together. You have the population intercept and the subject-specific intercept. And I'm also simplifying this model, so I'm assuming right now there's only one covariate. So, and that xi covariate is time, is a covariate that is just describe is time. And so when you have your only one covariate and that covariate is time, then your beta for that covariate, which in this case is beta 1, describes patterns of change in the mean response over time in the population of interest. And the subject-specific intercept, BI, represents the ith individual's deviation from the population mean intercept after the effective covariates have been accounted for. So in this picture, in this example, we have the outcome on the y-axis and time on the x-axis. And we have this, in this black line here is beta 0, that's the population intercept. And then the values for one subject, the dots are their actually observed data, and the line is their fit for the random intercept model. And so the beta 1, which would be the subject-specific intercept for the first subject, is just the difference between beta 0 and that blue line there. So in general, subject 1 has data points that are higher than the population average, which is that black line here, that slope. So their intercept is going to be higher than the population intercept. And for subject 2, the intercept for subject 2 is the difference between their intercept here and the population intercept, beta 0. So that's going to be beta 2, the subject-specific intercept for the second subject. And so what this model is saying is that, okay, we have a population slope, beta 1, and a population intercept, beta 0, and that line characterizes the population mean, describing the association between time and the outcome here. And because of this random effect, we can vary, basically shift that line up and down for each subject depending on where their data falls. So that's all that the random intercept model is. It's basically a regular linear regression, but you can shift the line up or down depending on the subject-specific data. So for that model, we can calculate a subject-specific and population-level mean, which I talked a little bit about in previous slide, but this is specific to this time model. So for the subject-specific mean is the expectation of yi given the beta I for that subject, and that's calculated by taking this set of values here, and then the population level mean. You can take the expectation of that. This is called iterated expectations, by the way, and there's a law of iterated expectations that tells you how to take a double expectation like this. And by doing that, you can get a population level mean as well from this model. And one thing that I'm going to note here is that this works. You can get a marginal interpretation or a population level interpretation from a linear mixed model. But when you have non-normal data and you start to put a link function around it, like we did with GLMs, that won't always be the case. And we'll talk about that in a few weeks. So we also get variance estimates from this model. And you may recall me saying that with longitudinal data models, we partition the variance into subject-specific and components and between subject components. So the total variance for this model is going to be sigma squared b plus sigma squared, and I'll show you where that's coming from. That's coming from the fact that if we want the variance of yij, I'll do that up here, that's going to be equal to the variance of beta 0 plus beta 1 plus beta 1 Tij plus error ij, which is equal to the variance of beta 1 plus Eij. And so the reason that the fixed terms drop out is because the variance of beta 0 is going to be equal to 0, and the variance of beta 1 Tij is equal to 0. That's just an assumption that's coming from the fact that we're treating these betas as fixed. For effects that are fixed, you don't have variance. Okay, so that gives us variance of bi plus epsilon ij. And we made an assumption that bi and epsilon ij are independent, which means that we can split up the sum of the variance like this. Oops, that should be a plus the variance of epsilon. And then also from the assumptions of this model, we said that the BIs have a normal distribution with variance sigma squared b. So that's going to be sigma squared b. And we also said that the epsilons have a normal distribution with 0 and sigma squared. So that means that the variance of epsilon is going to be sigma squared. So that's where that variance is coming from for the Yij. Similarly, we can get the covariance of each Yij and Yik term. So that's the covariance within a particular subject. What's the covariance across subjects? So say Ij and Ylj. Well, that's going to be equal to 0 because we assume that subjects are not correlated, that subjects are independent from each other. Okay, and then from the covariance, we can also get the correlation, which is given by the variance of the random effect over the total variance. So this correlation, this sigma squared b over sigma squared b plus sigma squared, is also called the intra-class correlation coefficient. And it can be useful because it tells you how strongly observations within a subject are correlated relative to the overall population. And it also tells us what proportion of variability is within subject variability. I personally think it can be helpful to visualize this ICC. So I'm just going to give you sort of a toy example here. Let's say we have a plot where we have individual slope lines for 3 different people. And their data points for each subject fit pretty tightly around these different lines. This would be a situation where we have high ICC. Which means that there's strong correlation within a subject. Alternatively, say we have something instead where we have lines for 3 subjects like that, but their data points are much scattered, a lot farther away from those lines and maybe even overlap with each other. So our our fits for the data might be more kind of all over the place rather than tightly around that regression line. And this would be a case of a smaller ICC. And we'll see some examples of that when we start doing this in R. But if you think back to the data sets that we looked at in the Intro to LDA lectures last week, The pig weights data might be something that's an example of a higher or a larger ICC, and the CD4 data would have a smaller ICC. So before we move into the next model, I want to give a quick summary of the random intercept model. And this summary here assumes a single predictor, which is time, but you can also have random intercept models with other covariates as fixed effects. And you can also include other random effects. But when you have a simple model like what we've discussed here, the random intercept or subject-specific intercept is the, by the way, that those terms are interchangeable, is the expected value of the response for each subject at baseline. The model assumes that the mean response will change over time in the same linear fashion for each subject. So if the population average relationship between the x and y is like this, then each subject has the same slope. It just is shifted up or down from the mean. If we assume the within subject residuals are independent, then this model is equivalent to a marginal model with exchangeable correlation structure. We haven't talked about that much yet, but there is a link between certain linear mixed models and certain GEE models, which we'll learn about in next week's set of lectures. And then this model also allows us to estimate the proportion of variation in the response that is attributable to the differences across subjects relative to the variation over time within a subject. And that can be useful for interpretation purposes. So the next model that I'm going to discuss is the random slope model, which is very similar to the random intercept, but now we allow subjects to have their own slope as well as their own intercept. These models I'm going to show you are going to have two random effects. They have both a random intercept and a random slope. Generally, when we add a random slope to a linear mixed model, we also include a random intercept, though this isn't necessarily, you don't have to, it just tends to be what we do in practice. And this is good for data where both the rate of change over time of the outcome as well may be good for data where the rate of change over time of the outcome may be subject specific, and you can still get an interclass correlation coefficient. So again, I'm taking a simpler form of the model where the only covariate is time here. And the random slope model for this is given below. So we have the same outcome, Yij, and we have Tij, that's your x, your covariate. And we have a beta 1, a slope for that x. We have a beta 0, a population level intercept. We have the beta 0i, that's the random intercept that we learned about in the previous few slides. But now we also have a b1i. So, and what that is that's the subject-specific random slope. And we have that multiplied by the Tij, by the time variable, because we want to indicate that slope is a slope on the time variable. You can have a random slope on other variables as well. But written out here are some of the model assumptions. We assume that the random intercepts have a normal distribution with some variance, which I'm going to call variance, that variance, sigma squared 0, 0. We also assume that the random slope has a normal distribution with mean 0 and its own variance, which is different from the variance of the intercept. And then we assume a correlation or a covariance between the random slope and the random intercept. So that if you wanted to take the variation of the vector of coefficients, vector of random effects, beta 0i and beta 1i, that would follow a multivariate normal distribution with mean 0 and the given variance covariance matrix of sigma squared 0, 0, sigma squared 1, 1, sigma squared 0, 1. So that places a multivariate normal distribution on the vector of random effects. And we're also still assuming that the measurement errors epsilon come from a normal distribution with sigma squared. So, and we still assume that the measurement errors are independent of each of the random effects. So we guess from this model, we also get a conditional and marginal mean of Yij, where the conditional mean is interpreted as the subject-specific mean, and the marginal mean is the population mean. The picture of what this model looks like is slightly different, however. This is similar to what I showed before. You have some outcome y, and then the response, the covariate in this example is time. This here is the population mean line, which has some slope and intercept. Say so you have two different subjects that are shown, and the fit through here is the subject-specific mean for that subject. And it's going to have a subject-specific intercept, which is the difference between the intercept from the population here and the start of that line. And it's also going to have a subject-specific slope. You can see that this slope is a little bit steeper than the population slope here. And that slope is going to be given by B1A. We also have a second subject whose intercept is B0B, which is the difference from the population intercept, and they have their own slope as well, which is a little bit shallower than beta 1. So you can see now when you have a random slope model, each subject can vary from the population average by both the slope and the intercept of their individual line. And what is the actual slopes of each of these lines? Well, the population one, and this is from the previous slide, is going to be beta 0 plus beta 1 times time. For subject A, it's going to be beta 0 plus beta 0A, their subject-specific intercept, plus beta 1 times time plus their subject-specific intercept, beta 1A times time. And for this line, it's going to be similar as what we did for subject A, where it's the population average, beta 0 plus beta 1t, plus their subject-specific effects is what gives us their regression line. So subjects vary not only in their baseline level of response, but also in terms of the change in their response over time. So I just want to bring it back to the general form of the mixed level effects model, just as we wrap up this portion of the lecture. So we talked about this in the previous lecture. There's a general formula for the mixed effects model. And both the random intercept and random slope models fit into this general form, where the covariates that you have, that you're putting random effects on, are given by the C matrix. The BIs are the random effects, And then your xi betas are your traditional terms from regular linear model. And then we also assume certain distributions for our random effect and our vector of error terms. And so practically, when you choose your random effects model, the columns of Zi, or things that you're putting random effects on, are typically a subset of the columns in xi. So you're not going to say have like sex and gender in your model for and model those as random effects, but not also include them as fixed effects. Like if you include them as random effects, you're usually including them as fixed effects as well. You can get the marginal mean, or also known as the population level mean for your data, which is just x beta. And you can also calculate a marginal covariance, which I'm not going to derive, but I'm giving you the formula of that here. And then any of the parameters that you're interested in, the betas, the fixed effect parameters, the population parameters, can be estimated using either maximum likelihood or restricted maximum likelihood. Generally, restricted maximum likelihood is used because it's less biased in this context. I'm not going to go too much into what the estimation of that actually looks like, but it's something that you'll go into if you take the longitudinal class next year. And one thing to know is that estimation can actually get quite complicated in mixed effects modeling. And finally, I want to talk about multi-level models. So multi-level models are a generalization of random effects models. In the previous examples, we've only looked at things where we have longitudinal data, that is, the subject is measured over time and correlation is due to repeated measurements in time. However, multi-level models are a generalization of that, where data within a subject or other unit is correlated due to repeated measurements, but that correlation need not be in time. And I want to add here that this is a generalization of random effects models for longitudinal data. So for multi-level models, the repeated observations don't necessarily have to be taken in time. However, we can still use random effects models to model the correlation within repeated measurements on the same subject. And some examples of what that data might look like are model students within a class. Say you're interested in test scores, and you have multiple different classes, and you have students in each class, and you think that test scores might be correlated within a class. Another way that you could have correlation like this are you have multiple families and you have multiple members in each family, and members within the same family might be correlated, or patients in a hospital, or etc. So it's just good to know if you see something about hierarchical structures or multi-level models that can be modeled using the same sort of random effects framework that we're using here. And so in the next set of lectures, we're going to cover some practical examples of random slope and random intercept models in R.